Good morning everyone. We are doing chapter 10 part 1, which is on sound waves. And for this chapter in particular, we are doing this guy and this guy. Okay, so this is your learning outcome. You have to know how to calculate the frequency, wavelength, and velocity of sound, calculate the intensity of sound and sound level, solve the Doppler effects problem. Sorry, my chair is not moving well. Explain and solve resonance in strings and air columns. So this will be your first part, and this will be your second part, and this will be your third part for chapter 10. And what should I say just now? Okay, never mind. If I remember, I'll tell you. So sound waves are longitudinal waves traveling through a medium. And remember, we have done this before. We have learned what is longitudinal waves. It is when we have a type of wave where the particles, the propagation, right? The propagation of the particles is parallel to the energy. Okay, and we have seen this with a string when we compress it and when we stretch it. So that is when you have longitudinal waves. So sound is a type of longitudinal wave, alright? Okay, so we have categories of sound wave. So we have the audible, which is what we can hear. Okay, what we hear is audible waves, and it ranges from 20 to 20 kHz. So 1000 is kilo, right? So 20 Hz to 20 kHz. This is the normal range of the human hearing of the human ear. And then you have infrasonic, that is below 20 Hz, and then you have ultrasonic, which is above 20 kHz. So if I were to plot this, if I were to arrange this, I will start with infra, and then I will start with, and then I will go for audible, and then for ultrasonic. Let me make my pen smaller. So infra is, so audible, you know, it's from 20 to 20 kHz. So this guy is more than 20 kHz. And of course, infra is below than 20. So this is below than 20. Okay, so you have infra, audible, and ultrasonic waves. Okay, next one. So this is just a figure that shows you infra. You start with infra, and then you continue with acoustic, and then you continue with your ultrasound, right? And the one that you use in medical equipment, such as ultrasound, you check for the baby. I hope no one has checked their baby in their tummy yet, because that's just not right at your age. So we have the ultrasound, right? Ultrasound, the frequency that is used is above 20 kHz. And you also have bats. Bats emit ultrasound to know the location of the things around them, right? They emit us ultrasound, right? So you can use sound to determine the location. You can use sound to have imaging, which is what you have when the doctors scan for baby. You should not scan your baby. Okay, next. So the speed of sound is higher in solids than in gases. So V in solid, right? The V of sound in solid is faster. Is the fastest. And then it is the slowest in gas, which means that what we are hearing right now, which is in air, which is in gas, is the slowest. So if I were to put something at my ear, which is a solid, and I tap it, I would hear a very fast version of that tapping. Whereas if I tap on the what do you call this, table, and I'm hearing it where the medium is air, right? The speed is slower. Okay, again, I'm gonna say this again. So I have an object, right? I have an object. This is a solid, and I'm tapping. So the speed that I'm hearing, the speed of the sound that I'm hearing is faster compared to when I'm tapping like this, because now the medium that the sound propagates before it reaches my ear is air. So that is when the speed is the slowest. Okay, so that's just a fact for that. So the speed of sound is the highest, is the most fast in solid, and it is the slowest in gas. Okay, so we have a picture here. Not sure if this is very intuitive to see. I don't know what this means, but fast, slow, average. Next, so the speed of sound in a solid rod is given, okay, so in solids in general. So this is the equation for speed of sound in solids. So you have the Young's modulus and you have the density of material. So I'm not sure if this is in your book, but just remember this equation, V equals to Y over density, square root the whole thing. And then we have another equation for the speed of sound in a liquid, right? So that's V equals to bulk's modulus over the density, and you are square root the whole thing. So that is your equation. And the most important equation is the speed of sound in air, which we will use over and over again for this particular subchapter. So V is equal to 331 meter per second. This is your V naught, which is the speed of sound in the air at 0 degrees. And then you have the temperature in Kelvin units over 273 K. K is Kelvin. You square root that. Alright, so if I ask you what is the speed of sound at 27 degrees Celsius? So what you should do is you have to convert this degrees Celsius to Kelvin, and 27 plus 273, this is you have to add 273 to convert it to Kelvin. So now it becomes 300 K, right? So how do I use this equation? V equals to 331, that's my V naught, and 300 over 273, and then you use your calculator, and whatever that value is your speed of sound when the air has a temperature of 27 degrees Celsius. Oops. Whoa. What happened? Okay. So, I'm going to go over this example again. So, what if I want to know what is the speed at 0 degrees? Right? Here they said 331 is the speed of sound in the air at 0 degrees. What if I want to find it? I just want to use this equation for 0 degrees. I can do that. So, what happens? So, this becomes, so 0 degrees is 273, because why? 0 degrees plus 273 is just 273 K. Okay, so this becomes 331 273 over 273 square root. So that's just 1, right? So the answer is V is just 331 at 0 degrees Celsius. We can use the equation to find out, but it's just a waste of time. So I'm just showing it to you so you don't have to do it again. Okay, so next, the speed of sound in various mediums at 0 degrees Celsius at 1 atm. Atm is pressure. Okay, so this is macam standard lah orang cakap. Tadi kita ada standard, which was the speed of sound in air, which is 331 at 0 degrees, right? So these are the other constants of the speed of sound in various mediums. So we have air, and we have air at 20 degrees. We have nitrogen gas, we have water, blood, muscle. You don't have to memorize this. Just showing it to you. Lead, copper, glass, aluminum, steel, wood. Right, if you see here, the ones that are solid, these are solids, right? The speed is high, whereas the speed of sound in gases such as nitrogen, we only have nitrogen and air, so these are low, and these are like mid-range, right? This is mid-range. So these are liquid. Sorry, muscle is solid. Oh, sorry, muscle is a combination of solid and liquid, so it's like in between, right? So these are solid, so the speed is very high, and then these are gas, so they are super slow. Okay, so the thing that you have to remember is the equation V naught is 331, and to find out the other speeds, of sound at various temperatures, various temperature. Ni untuk air sahaja. So it's 331 T over 273 square root the whole thing. T must be in Kelvin. That is your first equation. Okay, so let's do an example. So what is the speed of sound in air? Okay, we know the equation for sound in air at various temperatures at 27, 100 degrees, and 200. It's easy. You start with your equation. As always, start with your equation. You will get marks for that. So V equals to 331 apa tadi? Square root the whole thing T over 273. So that is your V. So now I want to find out what is 27 degrees in Kelvin, 100 degrees in Kelvin, and 200 degrees in Kelvin. So this is 27 plus 273, which is just 300 K. And I have 100 plus 273, which is 373 K. And the last one is 200 plus 273, which is 473 K. So just plug it in. 331 300 over 273, square root that. Get your answer for the 27. Then for V100 juga. So that is 373. 273, square root that. Like that. And your last one, V200, which is 331. So what is that? 473. 273, square root that. So that's your answer. Okay, so use your calculator correctly and you should get the answer like this. Okay, so 347 meter per second. Don't forget your units. This is your velocity. So you need to have your correct units. So at T equals to 100, convert it to Kelvin, and then your answer is 387. And the last one, the answer is 436. Okay, moving on. Okay, so this is the intensity of sound waves. Next subtopic. The average intensity of a wave is the rate at which the energy flows. The rate at which the energy flows. So rate of energy, you already know this by now. So E over T is P. So that's your power. Through a unit area, maksudnya through, selalunya denominator lah. So P average over A. Sorry, that should not be there. So I is equal to P average over area. Because this is your rate of energy. This is your through the area. Okay, so that's your equation. Through a unit area A, oriented perpendicular to the direction of travel of the wave. So the wave travels like this. This is the direction of the travel. It should be parallel to the energy, right? But the intensity is perpendicular to the direction of travel. So okay, let's see. So we have, this is my siren. This is a siren, right? So it's doing like that. So it emits sound waves. So this is this guy is on the floor. Let me draw this again. This siren is looking pretty bad. So this is my siren. Okay, siren. So the siren is on the floor, right? The siren is on the floor. Okay, so it's on the floor. And what happens is when it makes a sound, it will emit it like this. Okay, so what is this? Okay, so the direction of the sound is like this. This is the direction. Okay, and this is called, okay, benda Allah yang saya buat titik-titik ni, this is called the wave front. So this is the wavefront, the sound waves wavefront. Okay, so the wavefront is perpendicular to the direction of the wave of the sound. So the wavefront is perpendicular to the direction of sound wave. So wavefront is that. So kat sini, where is the wavefront? Is here. This is also a wavefront. This is also a wavefront. The whole thing is actually a wavefront. The whole thing. Okay, and it is perpendicular to the direction. Okay, so if your sound is moving this way, for example, I want my gray, please. Okay, thank you. So it's moving this way, right? In the x direction. Where is your wavefront? It is perpendicular. If I'm looking at this point, this is where it should be. Okay, so it's always perpendicular to the direction of travel. So you have your wavefront. This guy is your wavefront. Okay, and the direction of travel is just away from the source of your sound. Okay, what else? Okay, let me besarkan benda lah ni. Okay, besarkan jap. This needs to be discussed in detail. So, we have discussed what is your wavefront, which is the whole thing, right? That is perpendicular to the direction of travel. Between the wavefronts is your the distance between two wavefronts is your is your wavelength. Okay, so the distance between two wavefronts is your lambda or your wavelength. So this is one wavelength, this is your second wavelength, because it is repeating, right? So you have a wavelength, it's repetitive. And the whole thing is wavefront, wavelength. This is your source. What else am I missing? We have another term which is radius. So here I want to tell you that with a different radius you will have a different intensity. For example, I have a radio over here. Let's make this. Okay, I was going to talk to you about radius, right? So here I have a siren. Let's use this example again. Don't use the radio. So this is a siren or a radio. You can have either one. So it's the source of my sound, right? And I have wavefronts that are already labeled like this. And I am sitting over here next to the siren. And I have Meon sitting over here. And I have Humaira sitting over here. I don't know if Humaira and Meon are in the same class. Okay, but never mind. So, my distance to the siren is 1 meter. Okay, this is me, Nad. So, tadi ni Meon kan? Okay, and then this is Humaira. And this is Afika. Siapa lagi? This is siapa lagi? Meon kat ketiga ni. Okay, let's just say this is Hakim. Okay, Hakim. Okay, so Nat and Afika, Nat and Afika are both 1 meter away from the siren. Tapi Afika kat sebelah sana, saya kat sebelah sini. But we are listening to the same intensity of sound. Okay, so I am listening to the same intensity of sound dengan Afika because we are at the same radius from the source of sound. Now, with that statement, I can already say, okay, so Meon listens to intensity I3, whatever the value is. So Meon and Hakim will listen to the same intensity of sound. Will the intensity of sound be the same as mine and Afika? No. It will be slower. It will be less loud. Okay, the closer you are to the source of sound, the louder is your intensity. So I'm hearing, and me and Afika is hearing the highest intensity, and Hakim and Meon is listening to the less loud intensity, and Humaira is listening to the least, paling rendah, paling slow lah. Sebab lagi jauh kita daripada source, lagi slow lah kita dengar, right? So I'm listening to the same intensity to Afika. Hakim is listening to the same intensity of sound to Meon, and Humaira is on her own. Kesian. Tapi tak apalah, Humaira awak jadi example je. Okay, so the further away we are from the source of sound, the slower the intensity, yes. And then the intensity of sound is the same depending on the radius. Okay, so I am 1 meter away from the siren. Afika is also 1 meter away. We are listening to the same intensity. Hakim is 5 meter away from the siren. Meon is also 5 meter away. So that is why they listen to the same intensity. The intensity depends on the radius. Okay, intensity depends on the radius. Okay, so why does it look like a globe, right? Like a half, what do you call this? Sphere, half a sphere. Why does it look like a half a sphere? Because if I have a radio up in the air, right? This is a radio in air. Okay, so obviously the radio will make sounds. It's playing some song, and it will emit sounds like this. Remember, sound is a wave, so it will emit waves around it. And if I am down here, which is 1 meter away from the radio that is up in the air, and there is a guy in the aeroplane, no, not aeroplane, aeroplane dekat sangat. If there is a, what do you call that thing yang terbang tu, ambil gambar kamera semua tu, what do you call it? Drone. There is a drone that picks up noise, right? That if there is a drone that picks up noise, and the drone is 1 meter away from the radio, okay, so saya punya distance dengan drone ni sama daripada radio. The intensity of sound that the drone is hearing is the same as the intensity of sound that I am hearing. So if the drone listens to I1 intensity, I am also listening to I1 intensity of sound. Memang macam tu kalau kita letak kat udara, yang atas dengar, yang bawah dengar kan? Sama lah. So it's actually propagating radially. The sound is propagating radially. Okay, so sound propagates radially in the form of a sphere. Macam sphere. So that's why when I put the siren on the ground, it was half a sphere, because yang bawah ni ground. Of course ada juga sound, but I'm not interested in that sound because I can't be inside the ground, right? So when it is up in mid-air, the propagation of sound is radially dalam bentuk sphere. Okay, so what's the equation for that? So that is I equals to P average over area, and we should know what P is. It's energy over time, and your area is the surface area for a sphere. This is the equation for a sphere. Okay, please drill that in your head. So let's say kita tengok balik equation tadi. Ingat P over area, sphere. So now I am 1 meter away, and then there is another. This aeroplane is 100 meter away. This is an aeroplane. 100 meter is high enough or not? I don't know. So let's just say it's 100 meter. Let's not write it there. Susah saya nak lukis. Kalau lukisan saya buruk. Okay, let's use a different color for aeroplane. So this is blue. This is the aeroplane. Hope this is picking up. So it is 100 meter away from the radio. Anggaplah radio ni kuat gila sampai aeroplane pun dengar. So it's 100 meter away from the radio, right? It's up there, and I am 1 meter down from the radio. Radio ni suspended in air. Tak tahulah macam mana dia suspended. Just use your imagination. So if I were to calculate the intensity that I'm hearing, I nak so P average over 4 pi r squared, and I know what my radius is. It's 1 meter away from the source of sound. So I am 1 squared, and the intensity that is heard by the aeroplane is P average over 4 pi, and the radius from the source of sound is 100, right? So if I were to say what is the ratio of I naught to I aeroplane, I would say, I would just plug in this equation balik. So that's 4 pi 1 squared over P average 4 pi 100 squared. Okay, tak nampak pula. So, okay, jap. Let me drag this over. Give me a minute. Okay, so now I can cross it out because P average should be the same because P comes from the source. P average is the same because it comes from the source. 4 pi is a constant. It's just a number. So what am I left with? I'm left with 1 squared over 100 squared, which is just actually I naught over I arrow is R arrow. Benda Allah ni kat bawah, so R arrow is up here and R naught is down here. So the intensity is inversely proportional to the radius squared. So I is inversely proportional to radius squared. Tengok inversely proportional sebab radius kat bawah squared. Arrow pun terbalik, inversely proportional. So P average over 4 pi R squared. This is my R. So this guy should be down here, right? Kena letak kat bawah. And this guy is 1 over something. So this guy goes up here. So intensity is inversely proportional to 1 over R squared. So if my calculation confuses you, you should try it yourself. Okay? Okay, just now we talked about intensity, right? Let me just write down the equation. So I equals to P average over area. And the area should be 4 pi R squared, which corresponds to a sphere. The source propagates, the sound propagates from the source radially dalam bentuk sphere. Okay, so that's your equation. And the unit for intensity is watt over meter squared. Because area is in meter squared, P, power, is in watt. P average comes from your source. This is called intensity. We are learning a new term now. It's called intensity level. Okay, sound level or intensity level. Tadi intensity je, now it's intensity level. So the sensation of loudness is logarithmic in the human ear. Define beta. Beta is sound level lah ataupun intensity level. So beta is sound level or intensity level or decibel level of the sound. Okay, so decibel is something that we use a lot for my area. Decibel. So decibel is given by this equation, 10 logarithmic I over I naught. What is I naught? I naught is a constant whereby it is the threshold of human hearing. I don't know why I can't speak right now. So I naught is 1 times 10 to the minus 12 watt per meter squared, because you know intensity is power over area. That is the unit. So 1 times 10 to the minus 12. That is I naught. I naught does not ever change. You should always plug I naught into this equation. Okay, so for example, I know that I'm hearing a certain intensity of, let's say, 100,000. That's too much. I need a proper example. Okay, let's do an example. I hope there is. Okay, so dia kasih example kat sini. So threshold of human hearing is 1 times 10 to the minus 12, right? So if I were to plug in this intensity, the same intensity, this guy is I naught. So this guy becomes 1. Log of 1 is just 0. Right? Log of 1 is just 0. So 0 times 10 is just 0. So you get 0 dB. So this is the threshold of human hearing. You start from the base. This is the threshold of human hearing. You start from 0. And then as you increase your intensity, let's say 1 is your intensity, 1 over 1 times 10 to the minus 12, you log this whole thing, and then you times it with a 10, you will get 120 dB. Okay, so this is just an infographic of the different decibel sound level. So you have 0 dB, which is your threshold of hearing, and you have breathing, which is 10 dB. So when you breathe, you can actually hear it, even though it's very slow, right? It's not slow. Yeah, it's slow. It's very not loud lah. So you can hear it, but it's very minimal. So that is 10 dB from the base level of your hearing punya level lah. Okay, so you have rustling of leaves, which is also very soft sound. So that's 20 dB. Then you have your whisper, and then you have the sound of your refrigerator, and then you have moderate rainfall. And a conversation is typically 60 dB. And you have the car city traffic, which is kind of annoying, but it's manageable. And then you have a truck, which is very annoying. but still it's not painful yet. And then you have a hair dryer where it gets a little bit too much on your earrings on your hearing. And then you have the helicopter, which is like, oh, okay, that's gotta hurt somehow. Okay, it's close to the threshold of pain. So this is where your ear actually feels the pain. So at that intensity level, it gets painful. So at this point, it's already very loud, and nearing this point is when you start to, okay, I'm kind of feeling the pain, but it's not there yet, but it's almost there. Okay, so you have those different sound intensities. All right. So now let's find the intensity level of a busy traffic at 80 dB. So, okay, so here they are asking you what is the intensity level of a busy traffic at 80 dB. So they're asking I, and they are giving you dB, right? Patutnya dia cakap intensity je. Find the intensity of a busy traffic at intensity level 80 dB. Baru betul soalan dia. Okay, so we know the equation for intensity level is beta equals to 10 logarithmic 10 I over I naught. And the I is what we are finding, right? And we know what I naught is. I naught is the threshold of hearing, which is 1 times 10 to the minus 12 watt per meter squared. So that's your I naught. B is in dB. I is in watt per meter squared. So I must be also watt per meter squared. I naught is watt per meter squared. Alright. So we have that first equation. You should always write your equation before you start your problems. Okay. So find the intensity of a busy traffic at 80 dB. Okay, so 80 is given. The beta is given 80, and you have 10 here, log 10. And then you want to find what is I. You know what I naught is. 1 times 10 to the 12. To the minus 12. Okay? So what should you do? How should you solve logarithmic? And I know math is something that you are not great at, some of you. So 80, what I do first is 80 divided by 10 gives me 8, right? And then I have log 10 of I 1 times 10 to the minus 12. And then if okay, so remember, if you want to solve the inverse for a log, right now you want to make this guy an inverse, right? Because you want to solve for I. What happens? How do you do this? Because this is a base of 10, so you say 10 to the power of 8. Okay, so remember how you should do this. 10 to the power of 8 is equal to I over 1 times 10 to the minus 12. Okay, so 10 is the base of my log. 10 to the power of 8 equals to I over 1 times 10 to the 12. If I were to simplify this, I would say y equals to log 10x. Okay, so finding the inverse is 10 to the y equals to x. So this should be your equation to find your inverse of log. Okay, so what is the answer for this guy? So 10 to the 8 times with 10 to the 8 times with divided by, times with 10 to the minus 12, right? So that should give me 1 times 10 to the minus 4. So I is 1 times 10 to the minus 4. The unit for intensity is watt per meter squared. So that is the intensity of a busy traffic of 80 dB. Yeah? Okay, so that is the correct answer. Now we have a second question. Intensity of a level of jet engine. Intensity level je lah. Intensity level of jet engine is 150 dB at 1 meter. So dia kasih in dB and dia kasih radius. And then dia tanya what is the intensity level at 2 meter and 100 meter. Remember, the ratio that we learned just now, I1 over I2, is inversely proportional to radius squared, right? So this guy becomes R2 squared, R1 squared. It is inversely proportional. This is intensity, not intensity level. If they give you something in dB, you must convert it to intensity first. So let's do that. So beta, start with your equation. Beta is 10 log of I over I naught. And this will give you, let me rearrange this so we have some more space. Kita belah biarlah dulu. So that is 150. That's 150. I have 150 dB. I don't know, I don't want the radius yet. I just want to convert it to intensity first. So 10 log of I. Okay, so I of 150. I naught. I naught is 1 times 10 to the minus 12. Kan? Okay, so use the formula that I've shown you before. You should get your I intensity at 150 dB. As I'll use my calculator really quickly. The answer for that, if I'm using my calculator correctly, is 1000 watt per meter squared. So that is the intensity. Tadi kita convert intensity level to intensity. Okay, so now it's asking what is the intensity level at 2 meter and 100 meter. So before I can find the level, I must find the intensity at the different radiuses, right? So what is the intensity? So this guy is actually I at 1 radius. We want to find out what is the intensity at 2 meter. So this is I2 over I1, and I said intensity is inversely proportional to its radius. So radius R1 goes here squared. Radius R2 goes here squared. And I know what R1 is. It's just 1. And R2 is just 2. This guy is 2. This guy is 1. So I2 is in my calculator. I know what I1 is. I1 is 1000. So 1 divided by 4 times with the 1000. So I2 is 250, which makes sense because the further you are away from the source, the slower your intensity is, or the softer your intensity is. Okay, so it makes sense. At 1 meter radius, your intensity was 1000. At 2 meter, it became 250. Okay, so it makes sense. So now we want to find what is the intensity level. So we plug in B. Ajut tempat pula. Apa tadi? I2. 250 over 1 times 10 to the minus 12. So that should give you, that should be straightforward. So divide it by 1 times 10 to the minus 12. And then you log the whole thing. Log answer times with a 10. So the dB that you should get is 143.98 dB. That's your unit for your intensity level. So the dB, or the intensity level 2 meters away, is 143.98. Okay? Same thing for 100 meter. First, find out what is the intensity at 100 meter. Okay, so it's inversely proportional. So this is R1, this is R100. So square this and square this. So this becomes 1 squared, and R100 is just 100 squared. It gives you R100, and this guy is 1000. Intensity is 1000, right? So I at 100 meter is 1 divided by 100 squared times 1000 equals to 0.1. Okay, so further away, like 100 meters away from the source, your intensity just becomes 0.1. Initially it was 1000, and then it became 250 at 2 meters away. Then it became 0.1, 100 meters away. So now you find the intensity level. So that is 10 log 0.1 over 1 times 10 to the minus 12. Okay, so beta should be 1 times 10 to the minus 12, log the whole thing, times with 10. So 110 dB. Okay, it should be smaller, which is correct. So this is the beta for 2 meters away. This is the beta for 100 meters away. And this is the beta for 1 meter away. Okay, so we have our next example, the dB level at a distance of 2 meters from the sound source. So this is our sound source, and then it's saying 2 meters. It can be anywhere that is 2 meters. Okay, it can be here, it can be here, as long as it's 2 meters away. So the dB level at this point is 100 dB. What is the dB level at distances of 4 meters, 6 meters, and 8 meters? So what you should do is convert dB to intensity, right? So this is your first dB, dB 100, intensity 100. Sorry, let's just label it as radius. So this is dB at radius 2, and this is intensity at radius 2. And then intensity at radius 2, you want to find out what is the intensity at 4. So this guy becomes R equals to 4 squared. This guy becomes R equals to 2 squared. Okay? And you should find out what is I at 4 meters. Sama macam tadi, but you should try it yourself. It's the same thing. Memang sebiji. Okay? So this is the answer. If you want to try it yourself, this is the answer. Please check back if you got the same answer. Okay, so next example, the sound level 3 meters away from a point source is 120 dB. What is the sound source intensity and power? At what distance will the sound level be 100 dB? Okay, let's do this one because it's a little bit different. The sound level 3 meters away. Okay, so it's 3 meters away now. This is 3 meters. From a point source is 120 dB. So this guy is 120 dB. So beta 10 log I over I naught. This guy is 120, 10 log. I want to find out what I is. 1 times 10 to minus 12. So I at 3 meters is, let's do this one. So 120 divided by 10. 10 to the power of 12 is equal to that times with 10 to the minus 12. So the answer is 1. So I3 is equal to 1. Now I want to find what is the sound source intensity. So I want to know what is the sound source. Sound source. And I also want to know what is the distance that the sound level will be 100 dB. So let's do this one first. Baru kita tengok pasal sound source tu. So 100 dB, what is the intensity? So 10 log I over I naught. Okay, so 10 log, so solving for I that is unknown, Ix, we don't know the distance. So Ix is equal to, using my calculator, 100 divided by 10, and then 10 to the power of 10, times with 1 times 10 to the minus 12 will give me 0.01. Then use my equation for intensity. Ix over I3 equals to 3 squared over x squared, which I don't know what the distance is. And Ix is 0.01, I3 is 1. Okay, so Ix is 0.01, I3 is 1, and then equals to 9 over x squared. So solve for x. 0.01 divided by 1, 9 divided by answer, square root that, get x as 30 meters. Okay, you can check back. So 3 squared divided by 30 squared, and then we'll give you 0.01, which is the answer lah. Okay, so Ix equals to 30 meters is correct. So the distance should be 30 meters for the sound level to be 100 dB. So let's now find out what is the power. Lupa pula pasal ni. Power. Okay, so you know the equation for intensity is P average over A, where A is the formula for a sphere. Right? And we solved for I just now, which was, this was the I that we solved for, which was 1 watt per meter squared. So 1 watt per meter squared. P average is what we are finding out. Area is 4 pi, and the distance from the source was 3 meter away, right? So that is 4 pi r squared, and I was just 1. So solving that, I will get P average as 4 times pi times 3 squared. I will get 113.1 watt. Okay, these are my answers. Okay, so let's see the answer. So sound intensity is I equals to 1, we got that, and then we got the power, and then we got the distance R. Okay, next. Oh, dah habis dah, yay. Okay, so I'll see you in chapter 10, part 2. Take care.